In this presentation, I will share how mass of a body appears to be different with respect to different inertial frames of reference having very high relative speed. Relative variation in mass of a body means that mass of the body appears to change when it is moving with very high speed approaching speed of light. In order to prove the relation for relativistic mass, consider an inertial frame of reference S with respect to which position time coordinates are represented as x, y, z, t, and another frame of reference S dash with respect to which the coordinates are represented as x dash, y dash, z dash, t dash. Suppose initially at t equal to t dash equal to 0, both the frames of reference S and S dash completely coincide with each other, and then frame of reference S dash starts moving in x direction with a constant very high speed v approaching speed of light c, while the frame of reference S remains stationary. In the moving frame of reference S dash, consider an inelastic collision of two bodies A and B moving with same speed u along x-axis but in opposite directions. Suppose each of the colliding bodies has mass m and the bodies collides into each other after collision. If the collision mass 2m moves with speed v dash after collision, then by conservation of momentum, total momentum after collision must be equal to total momentum before collision. Means 2m into v dash must be equal to mu plus m into minus u. This gives us v dash equal to 0. That is, the collision mass remains at rest with respect to moving frame of reference S dash. With respect to stationary frame of reference S, suppose the bodies A and B appear to have mass values m1 and m2 and speeds as u1 and u2 respectively. After collision, as the collision mass is at rest with respect to frame S dash, so it will appear to move with speed of frame S dash with respect to observer in stationary frame of reference S. By conservation of momentum, total momentum after collision must be equal to total momentum before collision. That is, m1 plus m2 into v must be equal to m1 u1 plus m2 u2. As all the speeds are in x direction, so velocity addition theorem for x components of velocity of an object can be applied to velocities u1 and u2. Replacing ux with u1 and ux dash with u in this equation number 3, we get answer for u1 for body A, and similarly replacing ux with u2 and ux dash with minus u in equation number 3, we get u2 for body B as given in equation number 4 and 5. From equation number 2, we can write m1 plus m2 into v equal to m1 u1 plus m2 u2. Separating the terms with m1 on left hand side and terms with m2 on right hand side, and then simplifying, the result in equation number 6 can be proved. From equation number 4, consider the value of u1 as equal to u plus v whole divided by 1 plus v upon c square into u. Squaring and then dividing by c square, obtain answer for u1 square upon c square. After doing some mathematics, equation number 7 can be obtained. Consider from equation number 7, replacing u1 with u2 and v with minus v, equation number 8 can be obtained. That is answer for 1 minus v upon c square into u. Consider from equation number 6, m1 over m2 equal to 1 plus v upon c square u whole divided by 1 minus v upon c square into u. Using equation 7 and 8 for values of numerator and denominator in this equation, we can obtain equation number 9. Consider the special case if u2 is equal to 0, that is, if body B appears to be at rest with respect to stationary frame S, replacing m2 with m0. m0 means rest mass of the body. When body is not moving, its mass is said to be rest mass. Replacing m2 with m0 in equation number 9, we can write m1 equal to m0 whole divided by under root 1 minus u1 square upon c square. This result can be generalized as capital M is equal to capital M naught whole divided by 1 minus v square upon c square. So this is the relation for relativistic mass of a body when it is moving with very high speed capital V. Here capital M represents mass of the body when it is moving and M naught represents mass of the body when it is at rest. Thank you.